Hello students, welcome to Adobe's platform for class 12 physics. In this module, we will consider a current intensity problem involving inductor. Let us see what the problem is. So, an inductor of inductance L equal to 400 millihenry. This is 400 millihenry. 400 millihenry means it is, you can say 400 multiplied by 10 to the power minus 3 Henry. So it is 0.4 Henry, you can write, simple. So L equal to 0.4 Henry. And R1, R2 both are 2 ohm each. So R1 equal to R2 equal to 2 ohm are connected to a battery of EMF 12 volt. So these batteries, this is positive negative of the battery, it is 12 volt battery. The internal resistance of the battery is negligible. The switch S, there is a switch over here. The switch S is closed at time t equal to 0. What is the potential drop across L as a function of time? After the steady state is reached, the switch is opened. What is the magnitude of the current through the resistor R1 as a function of time? So, if we draw the circuit once again, you see it is, once again let me draw the circuit. So this is the battery, this is the switch, and this is resistance R1, this is the inductance. Conventional notations or symbols for resistance and inductance I am putting. This is a very simple circuit. This is L, this is R2. And this is the switch which can be made off and on. Now you see, if it is a simple circuit like this, only involving resistance, then what happens? So it is EMF, battery of EMF E, R1 is the resistance, R2 is another resistance. So when the switch is closed, this is the switch, say here, when the switch is closed at time t equal to 0, say, the moment the switch is put on, I call that time stamp as t equal to 0. The circuit looks like immediately both are 2 ohm, this is also 2 ohm, and this is a 12 volt battery, it is 12 volt battery. So what happens? The battery sees a parallel combination of 2 ohm resistance. So it sees a net resistance 1 ohm. Parallel combination of two ohm resistance is nothing but 1 ohm. And therefore, the battery sends 12 ampere current in the circuit, and it gets divided at this point into two branches. Here 6 ampere current flows, here 6 ampere current flows. And again they are combined and returns back to the negative terminal of the battery. So, and one more thing is that as soon as I switch on the switch, as soon as I put on the switch, immediately the current attains, in both the branch, current attains 6 ampere value. However, and before t equal to 0, that means just before switching on, the current through both the branches were 0. That means through a resistor, passes the current immediately after switch on, following Ohm's law. But as soon as the inductor is placed like this, inductor has an inertial property, you have learned from electromagnetics that inductor flux through an inductor cannot change instantaneously. Or we know that a current through inductor does not change instantaneously. That means if at t equal to 0 a switch is made on, then if the current through the inductor just before switch on, if it is I0 minus, it is a typical mathematical notation. That means just current through the inductor just before switch on, if it is I0 minus, is equal to I0 plus. That means the current just after switch on, the current through inductor in a circuit cannot change instantaneously. It happens, this inertial property is also there for capacitors and inductors, but resistance, they do not have such inertial properties. Immediately the current changes from 0 value to 6 ampere value in this case. But inductors, presence of inductors makes a little difference. Current through the inductor cannot change instantaneously. This is very fundamental when you are dealing with inductance. And initially, see, just before switch on, there was no voltage source present in the circuit because this switch is broken. Therefore, there is no, the circuit looks like just before switch on, the circuit looks like this only. This is R1, this is L, this is R2, and there is no presence of any voltage source. Therefore, in both the branches of the circuit, there will be no current. Current will be 0 in both the branches. Therefore, I0 minus 1, I can put 0. And therefore, immediately after switch on, you remember at t equal to 0, the switch is made on. So, I0 plus has to be also 1 by the inertial properties, by virtue of the inertial property of inductor. That means just immediately after switch on, there will be no current through this branch, this LR branch, series combination of LR. Through this branch, there will be no current. And inductor behaves like an open circuit at that moment. That means the behavior of, since there is no current through this branch, that means it happens as if it is an open circuit. That means immediately after switch on, the circuit will behave like this. This is E, this is R1, this is R2. And these are the two ends of the inductor, and these are the two ends of the inductor, and it is behaving like open circuit. That means the entire voltage, if I call these 2 points at A and B, these 2 points, then as if there is open circuit between A and B. That means at t equal to 0 moment, 0 plus this moment, the entire voltage appears across point AB, because between A and B, the potential difference becomes AE. But gradually, as time passes, the inductor starts conducting, and in the steady state, what happens? Inductor offers 0 resistance, and the circuit's behavior in the steady state looks like this. E, R1, R2. As if inductor, it's ideally inductor's resistance is 0, it behaves like a short circuit in the steady state, but in the beginning at t equal to 0 plus that moment, it behaves like open circuit. So it is t equal to 0 plus moment, and this is mathematically speaking t equal to infinity. That means when sufficient time has passed, the circuit looks like this. That means since both R1, since E is 12 volt, R1 and R2 both are 2 ohm each. So each branch 6 ampere current flows. So at t equal to 0, it is behaving, there is no current in this branch. But when sufficient time has passed, 6 ampere current flows through it. So initially after switch on, this particular switch, after AC is switched on, the current through this branch is a function of time, IT. Current through this branch, this particular branch. This branch has no this branch actually, it has no inductance, no capacitance. So it sees, this particular resistance sees 12 volt. Alright. Now, in the steady state, both the branches pass on 6 ampere current. But this branch, initially, the inductor behaves like open circuit. That means there is no current in this branch. But finally, what happens? It passes 6 ampere current because the inductor behaves like a short circuit. It offers no resistance when sufficient time has passed. So the circuit purely looks like a resistive circuit like this. So in this situation, when sufficient time has passed, mathematically I write t equal to infinity, 6 ampere current flows through it. Alright. And when initial condition, there is no current in this branch, but here it is a 2 ohm resistance put across 12 volt battery. So initially also here 6 ampere current flows. Alright. Now let us analyze the circuit in a mathematical way. This is a qualitative discussion, you can say. Now let us discuss the behavior of the circuit in a mathematical manner. How we can do that? At least we have understood that the current through this particular branch is a function of time after switch on. That means when the switch S is made on. Okay, switch on means the circuit is made on, that means I get a through path for the circuit. Okay, that means it is something like this. Now when it is switched on, so let us draw the circuit once again. This is R1, this is L, this is R2, and this is E. Now if the current through this particular branch, if I call it I as a function of time, why it is function of time, that you have explained, because initially after switch on, the inductor behaves like open circuit and IT is 0, and when sufficient time passes, the inductor behaves like a pure short circuit, offers no resistance, and the circuit behaves like a resistive circuit, and in that case R1, R2 being 2 ohm each, current IT becomes 6 ampere. So at t equal to 0 plus IT or I0 plus is 0, and at t equal to infinity, that means sufficiently large time, IT is 6 ampere. Now if I apply across these 2 points, the potential difference is E, because it's ideal battery. So I can write the voltage drop across inductor having inductance L is L di dt, that also we know, plus I R2, this is the potential drop across R2, has to be equal to E. This is pure Ohm's law or Kirchhoff's voltage law, you can say, when I am applying across these 2 points. Or what I can do, L di dt, just try to follow. So this is the differential equation involving I and T. I is the current through this branch of the circuit, is equal to E minus I R2 or di divided by E minus I R2 equal to dt divided by L. Let y equal to E minus IR2. Therefore, dy, E being constant, so dE is 0, so it is minus R2 di. Remember, I is a function of time. Therefore, y is also a function of time. So, di is dy divided by R2 with a negative sign. Therefore, from this particular equation, I can write dy by R2y is equal to dt by L, t being time. Therefore, or dy by y is equal to minus R2 by L dt. All right. So if I integrate both sides, then what happens? Let me remove this part. Now this part, let it be there. Okay, it is already there. So let me work out the steps in this space. So it is log y base E is equal to minus R2t by L plus K1. K1 is the constant of integration of this process. So y is equal to e to the power minus R2t so y equal to e to the power minus R2t by L plus K1. K1 is constant. So I get e to the power K1 multiply e to the power minus R2t by L. E to the power K1 is another constant. I call this constant K, e to the power minus RT by L. This is RT. Now, or I can write y is actually E minus R2. So, E minus IR2, E minus IR2 equal to K e to the power minus RT by L. So, IR is equal to E minus K e to the power minus RT by L. Or I can write I equal to E by R minus k by r e to the power minus RT by L. Alright, now at t equal to 0 plus, the current through this branch is 0 because I have already noted this. So I 0 plus is 0. So at that moment, if I substitute that value, that means what happens if I just remove this part. Let me write the differential equation as it is, keep the differential equation as it is, and apply the initial conditions. So in this expression, if I put t equal to 0 plus, then I is equal to 0. That means 0 equal to E by, this is E by R2. Here it is, this is R2. 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 Remember, this is all are R2 here. Here it is R2. Here it is R2. So at t equal to 0, 0 plus, this left hand side is 0, and this is E by R2 minus k by R2, and t equal to 0 plus, that means t equal to 0, it is e to the power 0, e to the power minus 0, e to the power 0, whatever c. That means it implies this quantity is 1, that means k is equal to constant of integration comes out to be e. So what happens? I t is E by R2 minus E by R2 e to the power minus R2t divided by L. Let me remove all these things from here to make some space. So finally I got this expression IT equal to E by R2 minus E by R2 e to the power minus R2 by L, or just substitute the values provided given IT equal to 12 divided by 2, R2 is 2, 1 minus e to the power minus 2L, 2T, sorry, 2T by 0.4 Henry. So it is 6, 1 minus e to the power minus 5T. So what we discussed qualitatively, at t equal to 0 plus, I 0 plus, from this expression, how much it is coming? 6 into 1 minus 1. Because at t equal to 0 plus e to the power minus 5t, that means e to the power minus 5 into 0, e to the power 0, which is 1, so it is 0. So I0 plus is 0, that qualitatively we discussed, and at this is at t equal to 0 plus. At t equal to infinity, what happens? I infinity, that means when sufficient time has passed, this quantity e to the power minus 5t, when t becomes infinity, e to the power minus 5 into infinity, that means it is 0, e to the power negative infinity. So it is becoming 6. So 6 unit is ampere, obviously. So as time passes, the current becomes in the branch becomes 6 ampere. That means what we discussed qualitatively, we are getting the same result from the mathematical analysis also. Therefore, what happens? The IT, the differential solution of the differential equation, which is this equation, is IT equal to six 1 e to the power minus 5t. So what is the question is, what is the potential drop across L as a function of time? So this is very simple. The voltage drop across the inductor, if I call it VL, VL is nothing but L didt, where L is 0.4 Henry multiplied by ddt of IT, that is ddt of 6 1 minus e to the power minus 5. So it is 0.4 multiplied by 6 multiplied by e to the power minus 5t multiplied by negative 5. And there will be another negative sign because this is constant. So ultimately there will be a negative sign over there. So 0.4 into 6, this negative sign comes here, and e to the power minus 5t when I differentiate with respect to t gives minus 5, and minus 5 e to the power minus 5t. ddt of e to the power minus 5t is negative 5 e to the power minus 5t, and these negative signs. So I get 2 into 6 into e to the power minus 5t, and unit is obviously volt. So it is 12 e to the power minus 5. So the voltage potential drop across L is 12 e to the power minus 5t. And you see qualitatively what is the value of this is VL, which is also a function of time. So what is VL 0 plus? That means just after switch on, what is the value of VL? It is this quantity is 1, that means it is totally 12 volt. What we discussed qualitatively, that means when the switch was made on, the entire voltage was appearing across L because L was opening as open circuit. Alright, so it is at t equal to 0 plus, it is 12 volt only. Alright, so if we remove all these things right now, so we have got the final expression for IT and VLT. Let me write IT and VLT's expression. Just after switch on, how the current and voltage, current through L, IT is 6 1 minus to the power minus 5t, and VLT, voltage drop across the inductor, is 12 e to the power minus 5t, and here it is ampere and here it is volt. And if I draw the curves of IT and VLT, what happens? You see, if IT versus versus T, IT at T equal to 0, it is 0, and then as T approaches infinity, this term becomes 0, so it is 6 ampere. So current increases, and finally in the steady state, as time is sufficiently large, this figure becomes 6 ampere. This is T equal to 0, and this is T axis. And what is VLT? VL means the potential drop across the inductance. Initially it is 12 volt, and then gradually it decreases and it becomes 0, because as T approaches infinity, limit T approaching infinity, VLT is 0. It becomes 0 almost. It takes infinite time to reach 0. It is asymptotically touching T axis, because when sufficient time has passed, inductors behaves like a short circuit, that means having 0 resistance. So voltage, if something has resistance 0, the drop across that is 0. But initially it is open circuit, that's why entire 12 volt is appearing across this, because this point is 12 volt point. Because you see Vt's expression at T equal to 0, it is 1, so it is 12. So it drops from 12 volt to 0 volt when sufficient time passes. This is VLT, and this figure is 12 volt. So whatever we qualitatively discussed, everything we could solve mathematically. Okay, now the first part of the problem is solved. That means what is the voltage drop across the inductor, and you also calculate what is the current through the inductor as a function of time, which is this thing. So these are the two equations. Now, after the steady state is reached, that means let us do this part of the problem. Steady state is reached means actually the circuit, here 6 ampere current is flowing, here 6 ampere current is flowing. Now switch is once again opened. So what happens? Let me remove all these things now. Let us redraw the part once again. Now, when steady state is reached, now we are just switching off the circuit. That means what is happening? The circuit looks like this. And there is nothing, because this switch is again made off. That means we are dealing with isolated part. Battery voltage is not appearing across this part of the circuit. But what happens if I again switch off time? assume that the switch off is made at t equal to 0 again. That means again I am counting a new time frame, new time scale. That means just before switch off, the circuit was looking like this. This is 12 volt and here 6 ampere current was flowing. Here 6 ampere current was flowing. That means in the steady state that we discussed earlier, 6 ampere is flowing in this branch, 6 ampere is flowing in this branch. So now suddenly there is a break, and this breaking moment I call t equal to 0. Okay, t equal to 0. At this moment the circuit is broken. So in this situation, do not confuse the t equal to 0 earlier part, just it is over. Now again I am calling this moment t equal to 0 as the switch off moment. So just before switch off, what was the current through this circuit, this part? If I call this current through this inductor, if I call it IT, then I0 minus is how much? It is 6 ampere again. Because just before switch off, the circuit was like this. The circuit was like this, and in both the branches 6 ampere current was flowing. Now therefore, when the circuit is again broken, that means it is switched off like this, then I can safely say from the inertial property of inductor or inductance, this will be 6 ampere. But now ultimately what will happen, since there is no voltage source, the entire current will die down to 0. So in the steady state, when there is no external voltage source, there is no voltage source present in the circuit, eventually the current will become 0. We can intuitively say. Actually now the circuit looks like okay, initially the current was flowing and at IT equal to 0 plus the current is 6 ampere, and this current is circulating and it will die down eventually to 0. Now if I apply, this is L, this is R2, this is R1. Now if I apply the Kirchhoff's voltage law, then I can write L di dt plus R2I plus R1I is equal to 0 because there is no external voltage source, no battery, no voltage source. So, or L di dt, since both R1 and R2 are 2 ohm, so I can write this as 2I plus 2I 4I equal to 0. Or I can write L di dt is equal to negative 4I. L is 0.4, so I can write 0.4 di by I equal to negative 4 dt. So di by I, steps are important. Di by I is equal to negative 10 dt. So if I integrate, this is di. So it is ln I equal to minus 10t plus k1. So I can write e to the power minus 10t into e to the power k1. So I call this as constant k again. So I is some constant k e to the power minus 10t. K is constant of integration. At t equal to 0 plus, I is 6 ampere. So I write, if I apply this particular situation, this particular initial condition, this is the condition what the inductance obeys. So 6 is equal to K. Because at t equal to 0 plus 10t is 0, e to the power minus 0 is 1. So I get K equal to 6. Therefore, I get I as 6 e to the power minus 10t. Six is e to the power minus 10t. Because once again there is just L di dt plus 4I is equal to 0, or this is 0.4 di by I equal to minus 4 dt, or di by I is equal to minus 10t. So ln I is equal to e to the power minus 10t into some constant of integration k at t equal to 0 plus I 0 plus is 6 ampere, because here just before the switch off, the current through this particular branch was 6 ampere. That's why it is 6 ampere. So if I write here, actually this is not ln I, this is I. Okay, I equal to, because from this I can write it is ln I is equal to e to the power ln I equal to minus 10t plus k1. So I equal to e to the power minus 10t into some another constant which is e to the power k1. That's why I write I equal to e to the power minus k e to the power minus 10t. At t equal to 0 plus moment, I is 6 ampere. Therefore 6 is equal to k e to the power 0, which is k only. Therefore value of k is 6. So I equal to 6 e to the power minus 10t. That means this current, when battery is removed because of switch off condition, R1, L, R2, and I have assumed that IT current is flowing, and since there is this part is removed because this is switch is made off, the same current is flowing in the loop itself through R1 also. So this current is flowing through both R1 and R2, and it is flowing through R1 in this direction. Alright, because initially the current through L was moving in this 6 ampere in this direction top to bottom. Immediately after switch off, the current through inductance cannot change instantaneously. The current through inductor has to be 6 ampere, and it passes through R2 as well as R1 because this part is removed, and this current IT, it is a function of time, and its expression we could find IT is equal to 6 e to the power minus 10t. As t approaches infinity, that means after switch off, if sufficient time is passed, IT becomes 0. because 6 e to the power minus infinity is 0. But at t equal to 0 plus moment, just after switch off, IT becomes 6 ampere only. So it is consistent with the qualitative discussion. So the current through the resistance R1 as well as the resistance R2, it is mathematically expressed as a function of time I equal to 6 e to the power minus 10t. So this is the problem. So that we have already found, and this is 6 e to the power minus 10t is the current magnitude of the current through R1 as a function of time, and the current flows in this direction, bottom to top. Okay, so it is a very interesting problem involving a very interesting property of inductance, which is what? That means the current through inductor cannot change instantaneously. So switch on or switch off, initially it was switched on, then after attaining steady state it was switched off. Switch on and switch off are instantaneous phenomena, but the effect of that cannot be immediately sensed by the inductor, whereas that can be immediately sensed by resistance R1 and R2. Okay, and this is the way you can solve the problem. I hope you have understood the problem. If you find any difficulty, please revert back to us. We will further explain to you, and we will consider few more such problems in our regular classes, and we will give you a collection of such problems so that you can work out and clear your doubts on these particular issues. Thank you for your listening. Thank you very much.